Okay, thank you for the introduction, and first of all, let me also thank the organizers for inviting me here to this nice workshop and giving me the opportunity to talk about some work that I've been doing in close collaboration with the Innsbruck ITAMP group of Rainer Blatt. What I will be talking about is open system quantum simulation with trapped ions. And before getting to the outline of my talk, let me just briefly motivate or point out a little bit the interest or my interest in open system quantum control and quantum simulation. So as we've seen in talks already by Hartmut yesterday or just right now by Alejandro, there might be different motivations of why we might be interested in open system quantum control. For instance, on a fundamental level, because it's just ultimately inevitable to have to completely isolate a system from its environment. But on the other hand, as we've seen in Alejandro's talk, we can also think of dissipation as a resource for certain purposes, such as dissipative preparation of entangled states and phases. Or what I will be focusing on is open many-body systems where new questions arise of how many-body dynamics takes place in an open system context. So I will be in this talk focusing on some work over the last years with respect to these two parts. And then there's, for me, another fascinating line, which is so far, I think, pretty unexplored, which is concerned of using, for instance, dissipation to do a new paradigm of quantum computing. So my talk is essentially also divided in two parts. In the first part, I would like to give you a short reminder or introduction on the concept of digital quantum simulation, and then show you how one can extend the more well-known concepts of Hamiltonian quantum simulation to an open system context, and show you some tools that we've theoretically developed and implemented together with the Innsbruck group with trapped ions, a complete set of tools to do in principle arbitrary Markovian open system dynamics. And then in the second part, I would like to introduce you to a new kind of scenario where one can ask us what new physics could one observe if one is able to engineer both Hamiltonian and dissipative dynamics in open many-body systems, and then show you some experimental results where we observed exactly the mentioned competing coherent dissipative dynamics with a few trapped ions. And what is another point that I would like to address in this context and along my talk is that I think it's pretty important to develop new tools and techniques to detect and to reduce errors in quantum simulations. So let me get started with the first part. I think I don't have to motivate much why we might be interested in quantum simulation. I think one of the motivations is that we would like to understand many-body quantum systems, and as you all know, this is pretty hard in general. But that there has been a lot of progress in using controllable quantum systems like cold atoms and optical lattices or trapped ions to study experimentally in a controlled context the physics of certain classes of models, as for instance spin models, spin model type Hamiltonians, for which trapped ions, for instance, are a particularly appropriate platform. And as we will hear later on today, I think, in various talks, there's been going on amazing progress, starting with the first theory works of Diego Porras and Ignacio Cirac in 2004, and then the first experiments on spin-type interaction model simulations by the Schatz group, and now by going to even always larger and larger system sizes, with up to a few hundred trapped ion spins in a penning trap, for instance. So I will be talking about the complementary way of quantum simulation, namely the digital approach or universal quantum simulation, where we actually will use a quantum computer that we don't have yet, at least not a scalable big one, which we can program at will, essentially, to explore the physics of interesting many-body models that we might be interested in. So yesterday we've already seen an introduction to the idea of the stereoscopic or digital quantum simulation by Christoph Wunderlich, where the idea for the Hamiltonian context, for instance, is that instead of trying to engineer directly a certain spin Hamiltonian that we might be interested in, that we actually encode our system in an array of qubits and then apply a set of gate operations essentially to approximate to a controlled degree the actual time evolution that would emerge from the Hamiltonian if we had implemented in a lab directly. And the main properties of this approach to a quantum simulation are the universality, as has been proven by Seth Lloyd, that it's efficient, and that in principle the errors that appear are known due to Trotter type decompositions with tight with strict bounds on the influence of errors. Regarding experimental errors, in principle, this approach, as it's based on a quantum computer, are also under control, at least in the future, in principle, as one might use quantum error correction codes. What I will show is that even not yet having a fully fault-tolerant quantum computer, one can also think about reducing experimental errors in a special purpose way. And as I'll try to show you, is that it's also not limited only to Hamiltonian dynamics, but that one can leverage these concepts also to a many-body open system context. So let me briefly just point out that the experimental demonstrations of these concepts that we have been developing have been done together with Reiner's group in Innsbruck, where one has a linear pole ITAMP setup with a set of high fidelity gate operations like addressed single stark shift, global rotations, and the high fidelity Mueller-Sørensen gates, which allow us essentially to implement any unitary dynamics on the system. On the other hand, there's another important ingredient, which is an optical pumping technique addressed, which will be the key ingredient to engineer in a stereoscopic way open system dissipative dynamics by applying this optical pumping technique to certain subsets of ions and having another set of ions encoding the actual system of interest. And then there is another whole bunch of tools that I will not describe in detail here, like hiding and unhiding techniques in certain states and other tools which complement this set of operations. So as I already mentioned, the main advantage of the digital simulation approach is, in my opinion, the flexibility with respect to the interactions of the model that I might be interested in. So what you see here is a 2-ion digital quantum simulation where time dynamics according to such Heisenberg type Hamiltonian has been implemented in a stroboscopic way, which means that the time dynamics is approximated by applying blocks according to the different non-commuting terms in the Hamiltonian stroboscopically. And as I would like to point out, is that, for instance, whereas the XX and YY interactions are directly accessible via Mueller-Sørensen gates in the Innsbruck setup, as that Z interaction, as already pointed out yesterday by Christoph, can then be achieved by combining the set of universal gates, like the XX interaction with some Y rotation sandwich, to realize interactions that are not directly underlying the actual interactions in the Hamiltonian in the simulator. So there's a whole set of other experiments that have been done in this direction in the work by Ben Lennion and others. But I think that one of the main points, at least for me, is that one can use this digital approach also to simulate pretty exotic interactions, like, for instance, 4-body spin interactions, or time dynamics according to 4-body spin interactions, as is shown schematically here, where one can show that by just using 2 global Mueller-Sørensen gates, for instance, one can engineer n-body interactions, which usually requires 2n 2-qubit C0 gates, and which is for higher order interactions pretty pretty hard or impractical by trying to engineer them in an analog way, as Alejandro has pointed out. Although for lower body interactions, like 3-body interactions, there's, for instance, work by Alejandro where they looked into how one could get 3-body models in an analog always-on approach. What you see here is experimental results on the implementation of such 4-body unitary time evolution. You might ask, why might I be interested in such strange many-body interactions and not just the 2-body easing models? Well, these interactions are of interest, for instance, in topological quantum information processing, like Kitaev surface code, where one has Hamiltonians, where these 4-body plaquette-type interactions naturally appear, or in condensed matter models. And the remaining big challenge, if we are able to simulate such 4-body interactions, is also to ask the question, can we also engineer collective dissipative many-body processes, for instance, with the purpose of using these to achieve ground state cooling in such models, or the preparation of entangled states by dissipation. And I would like to give you a flavor on the next slide, in the next slides, how this works in a digital approach. So kind of the setting is as follows. We, on a formal level, is that we have our system coupled to an environment, and as we've seen already yesterday in Hartmut's talk, is that then if the system is initially uncorrelated from the environment, which, as we will see, can be achieved in the present context, then the time evolution is given by this so-called Krauss map, specified by such Krauss operator. So one special case would be just unitary dynamics on the system, where one has just U rho or U dagger, or as, also dissipative processes, as you will see in the following. One limiting case that is well known to all of you is the master equation limit, where one has some coherent time evolution of the system itself, and for instance some dissipative dynamics given by such Lindblad term with dissipative rates and quantum jump operators, which can be of many-body nature, as you will see in the following. So kind of I would like to give you an idea of how one can use the digital toolbox to engineer also these many-body dissipative maps. And kind of the idea is as follows. Imagine that you have a 2-level system where you an excited atom, for instance, in a metastable state, and you all know that after a certain time, if you wait for long enough, the system will be automatically pumped into this ground state. And kind of the idea is that we want to transfer this concept now to a many particle context, for instance, such 4 spin atoms that might sit on one plaquette appearing in this Kitaev model or something like that. And that the goal is that we would like to dissipatively pump the system collectively from the -1 into the +1 subspace of such 4-body operator. So imagine that you have, for instance, one plaquette with these 4 states. The goal would be that all these excited -1 eigenstates of this 4-body operator are converted unidirectionally into +1 eigenstates. So formally, what we can write down is similar to a quantum jump operator appearing in the master equation for a damped 2-level atom, formulate some collective 4-body quantum jump operators which have this form, where you see that they first of all act on all 4 qubits simultaneously, and where you have here a projector onto the +1 eigenstate of this 4-body operator, such that if you apply it to any +1 eigenstate, like this example, it's annihilated, so +1 eigenstates are dark states, whereas if you apply it to a -1 eigenstate, sigma z operation in this case converts this state into the +1 state. So I mean, writing down this theoretically is simple, so to say, but how can one achieve this now in an implementation? So, and this can be done by a quantum circuit involving an ancilla qubit, as Alejandro already mentioned in his talk. So imagine that you have your 4 system qubits and an ancilla prepared in initial state, let's say 0. What we first can do then is apply a mapping, in this case in the ion trap realized by 4+1 ion Möllmer-Sørensen gate, to map the information whether the 4 qubits are in a +1 or the -1 sector of the Hilbert space onto the 2 logical state 0 and 1 of the ancilla, so shown as here and shown in this example. And then if we in a second step apply a controlled gate operation, where we apply only if the ancilla is in the state 1 sigma z rotation, we can convert this state into a state belonging to the +1 sector with a certain amplitude. After undoing this mapping and resetting the ancilla qubit to 0, one then can show that this actually corresponds to a dissipative map where we have pumped our 4 qubits collectively from one sector into the other. And as you can see is that in this digital approach, I can now control the strength of this dissipative dynamics by changing, in this case, this parameter. For very small phases, we essentially do only, with a small amplitude, this conditional spin flip, whereas if we choose it for pi over 2, then we deterministically realize pumping from one sector into the other sector. The final reset of the ancilla qubit is, for a theoretician, just looks like this, and this is how it's done in an experiment in an Innsbruck setup by doing a pi pulse from this logical D state here, and then a subsequent optical pumping to the 1 state. And this is the physical ingredient where we kind of use the Markovianity, if you wish, of optical pumping of a single ion to achieve, in combination with the many-body gates applied to the whole register of ions, Markovian collective dissipative dynamics on our system qubits. Here's an example of how one can use this for dissipative preparation for 4 qubits in an entangled state. So the idea would be that we try to realize this pumping, as I explained, for this 4-body operator by pumping into the simultaneous +1 eigenstate of a set of commuting stabilizer operators, in this case these 4, such that the only unique dark state of this collective dynamics is, in this case, this entangled 4-qubit G at Z state. So starting in a fully mixed state, this is an experimentally reconstructed density matrix, where you see that all populations appear with the same amplitude and no coherences are present. We realize then by this digital method, as I pointed out, a sequence of pumping steps deterministically, such that ultimately the system is driven from any initial state to the unique target, in this case G at Z state. What I will not explain is that whereas these things have been open loop dynamics from a quantum control perspective, that means that we've at no point measured anything at the system, but everything has gone kind of automatically by quantum feedback from the ancilla onto the system. One can also realize a QND readout of many-body observables by, for instance, mapping this information of a many-body stabilizer operator onto an ancilla, hide other ions, and read out the ancilla ion to get some information, for instance, about these expectation values, which are important in the context of quantum error correction, for instance, in topological codes. So with this, I would like to conclude the first part, and now in the second part, think about 2 things, namely of how we can now use this toolbox of operations to explore the physics of a new many-body system, or a many-body system where we can engineer at the same time coherent and dissipative dynamics. So kind of putting the tools that have been individually demonstrated now together and run an open system quantum simulator, and at the same time see what the dominant errors will be and how we can find counter strategies to reduce their effect. So to set out the stage, let me think about the following situation: that you, for instance, have a master equation where you have some Hamiltonian dynamics and some dissipative dynamics that are non-competing, incompatible among each other. Just as you know from a Hamiltonian context. For instance, if you think of the Bose-Hubbard model, where you have 2 terms in the Hamiltonian which favor different types of orders. For instance, a tunneling Hamiltonian prefers the system to have a completely delocalized state of particles over a lattice, whereas then the on-site interaction prefers a state where particles are localized and favoring the mod insulating phase, for instance. So here in this open system context, the idea is similar. We can ask the question, can we engineer some dissipative processes that drive our system to an ordered state, which, for instance, enhances the phenomenon of superfluidity, and then add an interaction Hamiltonian, which corresponds to coherent evolution that is incompatible with the tendency of the dissipation to create order in the system. And then we can ask whether there is when one might observe in a many-body system, then a phase transition as a function of the relative strength of these two tendencies. And one model, which has been studied by Sebastian Diel and the group of Peter Zoller, for instance, was a model of bosons in an optical lattice, where a dissipative dynamics was formulated that delocalizes particles over a lattice. So what one has here is a quantum jump operator, which acts on a boson, let's say at this lattice site A, and delocalizes it dissipatively and drives it into a superposition of being at the left and the right lattice side at the same time. If you run this dissipative dynamics for a certain number of particles initially present in a lattice, then the system is for long times driven into a BEC where particles are delocalized over the whole lattice. Now imagine that you switch on at the same time the normal Hubbard-type interaction Hamiltonian, where particles interact, provided that there are more than two or more on a single side. Then this is a Hamiltonian that competes with this tendency of the dissipation to wash out particles over the lattice, as it asks kind of locally how many particles are sitting on a certain lattice side. And what has then been analyzed in theoretical work is that indeed in a mean field Gutzwiller treatment for the density matrix, that the system that there's going on a phase transition from a phase where for dominant dissipative tendencies the system is driven to a steady state which exhibits superfluid behavior, whereas if the interaction strength overcomes a critical value, then the system ends up in a thermal state. Whereas there are ideas how to engineer such dynamics for cold atoms in an optical lattice. This is still quite challenging, and this was our motivation to ask, can we implement similar dynamics by now considering a model where we simulate these bosonic particles by spins in an ion chain, and where we can observe similar competition physics in a spin model. So this is kind of a translation table where you see that we can substitute this bosonic two-side jump operator by a two-spin quantum jump operator, where in spin excitation, so spin up excitation on one side is dissipatively delocalized and driven into a superposition of the spin excitation residing on both sides. And then depending on the number of initial spin excitations in the system, after long times these spin excitations are delocalized and drive the system into an entangled state, in this case a Dicke state, depending on the initial number of excitations in the system. Now, as we are treating here with spins, this corresponds to hardcore boson or the hardcore boson limit. Here we cannot simulate more than one particle on the same side, and that's why we identify or we replace the on-site interactions for non-hardcore bosons by a spin-spin interaction of two bosons sitting on neighboring sides. To observe the dynamics, then we apply now stroboscopically dynamical maps which combine dissipative steps with coherent dynamics. So what in the practical implementation, what one can do is, in order to avoid shuttling of ions, one can park kind of all system spins that are not participating in an individual dissipative step by spectroscopic decoupling and parking them in decoupled electronic states where they do not see the operations applied globally onto the ion chain. then the elementary dissipative maps for these two quantum jump operators can be implemented in a digital way similar to the stabilizer pumping that I've shown you before, such that the system is deterministically pumped into this superposition state shown here. After applying a composite dissipative map acting on all pairs of neighboring spins over a system, one can then apply also coherent dynamics, which competes with this dissipative tendency, and as it's a spin-spin interaction, it's essentially equivalent to a Z-Z type interaction, which, as I've shown you, can be realized up to some low global rotations by a Mermer-Sørensen type interaction. And then the last part, what one can include is some error detection and stabilization techniques, of which I will speak in a few minutes. If one then does some numerical study of the dynamics, for instance, starting in a 10-spin system with 3 excitations initially present in the system, then what one sees, if one applies these dynamical maps iteratively, that the system is driven, if one has purely dissipative dynamics, indeed into these Dicke states, which correspond to the analog of a hardcore particle Bose-Einstein condensate in the system. And to the extent as one increases the interactions, which are controlled by this phase parameter here, one sees that in a steady state, the system approaches a state where this delocalization of spin excitations is suppressed more and more. Here's then a kind of zoom in, where one sees that in this particular building up of the combination of dynamical maps, the dissipation tries to build up the coherence in the system, whereas then the Hamiltonian, which always sets in here at the end of the dynamical map, then partially destroys the build-up coherence. These are then experimental results where we studied this with 3+1 ions, 3 system ions, starting in an initial state with 2 spin excitations, where one sees that initially the system, this is the blue points, is driven into towards the 2 spin excitation Dicke state, but after a certain time, one observes that actually this saturates and the overlap with the actual target state of the ideal dissipative dynamics decreases. If we then combine the dissipative dynamics with coherent dynamics, we see that initially the system is, as before, driven towards the 3-qubit Dicke state. And then if the coherent competing Hamiltonian, which is active if 2 spin excitations are present on neighboring sites, then suppresses these dynamics as we've seen in the numerics before, and then subsequent application of another dissipative maps again builds up this coherence, and so on and so on. So as you've already seen, the main problem here is that that the complexity of this the implementation of these dissipative maps is that high that gate imperfections prevent us from observing the pumping towards these dissipative target states for longer and long sequences. And the reason is that that we encode our hardcore bosons or spins in this digital simulator, and errors in gate operations lead to a non-conservation of the actual spin excitation number. So whereas ideally I would delocalize let's say a single spin excitation over 2 sites, I will have some leakage into the sector with no excitations on neighboring sites or into the sector with 2 excitations on neighboring sites. And this means that over a sequence of dynamical maps, we actually leak out of the ideally conserved subspace of a certain number of initial spin excitations. If one takes this into account, and that the sequences are for a single elementary dissipative maps are already quite long, on the order of involving 20 gates or so, this is fully consistent with these imperfections and can be modeled rather accurately by a depolarizing noise channel as we average over many directions in the gate operation. So this motivated us to ask whether we can develop counter strategies to fight this problem that despite the ideal dynamics should conserve our initial spin excitation number, we kind of whether we can find techniques to run our system for longer simulation times. And the simplest idea would be to ask our system at the end of our simulation sequence, is it still in the subspace of the initial excitation number? And this can be realized also in a digital way by realizing a QND measurement of the spin excitation number in our system. So the key point of this measurement is that we apply a unitary operation which maps the information whether in our system there is exactly the right number of spin excitations onto the states of an ancilla, but without asking, of course, where these individual excitations reside along the chain. This can be done by such unitary operation, which we can again build up from our unitary simulation toolbox. This is then the results that one sees. The red points, if one at the end of the sequence performs this QND measurement and keeps only the results where one has the system still in the right excitation number subspace, one sees that one can extend the simulations to longer times and that the actual accuracy of the quantum simulation increases. On the other hand, this is kind of inefficient, at least it will certainly be inefficient for large systems where the chance to find the system in the end in the right excitation number subspace will be exponentially small. So kind of a more sophisticated counter strategy would be the following. Whereas if we do not do anything, we've seen that the system spreads out over all microscopic states. So for instance, in a ion chain, essentially we will on average have more or less 5 excitations present. So the idea is, can we implement a process where we actively pump back our system along the simulation into the desired simulation subspace, as shown here. And this is actually indeed what we did, is that we thought of how to implement a process in addition to the dissipative and coherent dynamics, which, for instance, extracts a spin excitation if there are more excitations in the system present than the desired initial value. And kind of the important thing is that, of course, we want to do this efficiently and also in an experimental sense by not using now a whole register of ancilla qubits. What we want to do is also to do it in an open loop quantum control version. That means that we want to have this correction scheme without the necessity of measuring, for instance, an ancilla particle and doing some classical feedback in order to avoid heating up of the ion chain and the need to recool it before applying other gates, for instance. And what we then developed is a fully automatic scheme, of which I would only like to give you the main idea. So the idea is, if we try to stabilize our system by extracting spin excitations that might be too many present in the system, we first do a mapping similar to the mapping described before, where we write the information whether we have too many spin excitations. So this is the projector to the subspaces with more than M0 excitations in the system by a pi rotation onto the ancilla. And now we implement a controlled operation where, if there are too many excitations present, we extract one excitation step by step until we've succeeded with this. And the important point is that we would like to achieve this in such a way that once we've been able to extract an excitation, this protocol stops automatically, even if we physically apply more pulses to the system. The key idea of this is that we try, as spin excitations are encoded as spin up and down are encoding the presence or absence of hardcore bosons on a lattice, we try to extract, if necessary, an excitation by a flip-flop operation, which can be realized by two types of Mermet-Zorans in XX and YY type terms, until we've successfully extracted an excitation and without disturbing the possible delocalization of the remaining particles in the system. Due to the lack of time, I will not go into details of this, but essentially the nice thing of this scheme is that we can reset, or that we can extract the ancilla from the computational subspace 0 and 1 once it has successfully extracted a system. And then the magic kind of the Mermer-Sørensen gate is that once the ancilla is pumped out from the computational subspace, the application of any further Mermer-Sørensen gate pulses physically to the chain will not have any effect anymore. Then we tried to do this in an experiment by going into this, by preparing an initial superposition states where for 3 qubits all microstates, all 8 microstates are present, and all coherences are also present in the system, and then applied this extraction protocol for a stabilization of the system in a subspace with, for instance, 1 excitation. And as you can see here, this protocol does indeed what one expects, namely that it pumps out all population in a single step with 3 excitations in the system to the 2 excitation sector, and what is in the 2 excitation sector is added to the 1 excitation sector, and the vacuum sector, if you wish, remains untouched. The quality of these operations at the moment is not high enough to be included in situ along the simulation, as I've shown in the numerics. But I think it's a proof of principle that one should think about such a special purpose quantum error correction protocols, which might allow one to extend simulation times to longer times before we actually have a fully fault-tolerant quantum simulator at hand. So with this, I would like to conclude and hope that I could show you that there's quite some progress also going on, despite still in small systems, of course, an open system and digital quantum simulation with trapped ions, and that there are both experimentally and theoretically new non-equilibrium many-body physics scenarios, and that it's, in my opinion, worth and necessary to think about special purpose error detection and reduction protocols to make some more progress in the direction of reliable quantum simulation of larger systems. With this, I would like to mention and thank the collaborators with whom I've had the pleasure to do this work that I presented to you. Julio Barrero, who was the leading guy in the open system quantum simulation toolbox, Philip Schindler on this dynamical maps project I've been talking to you right now at the end, Cornelius Hempel and Ben Lanyon on the trotterization experiments, Rainer Blatt, Christian Roos, and on the theory side, Sebastian Diehl and Peter Zoller, and the whole Innsbruck ion trap team. With this, I would like to thank you for your attention.